every function whose derivative is little f of x, or we can think of that as capital F prime of x, is an antiderivative. We'll call these functions a family of functions, and they're defined by capital F of x plus c. A different value of c here will lead to a different member of that family. So mathematicians represent this idea symbolically using what's called the integral sign. And the integral sign looks like a snake on its tail, kind of like a cobra. So by writing the integral of little f of x dx, we're referring to all the antiderivatives of f of x. Another way to say this is you'll often hear this referred to as the indefinite integral, but a lot of times it's just shortened to integral. If capital F prime of x is equal to little f of x, then the indefinite integral of little f of x dx is equal to capital F of x plus c for any real number c. So this represents all the antiderivatives of little f of x. So the little f of x is the integrand, and that's just the derivative of capital F of x. Capital F of x is the antiderivative of little f of x. And of course the plus c is our integration constant. So in the scheme of things, starting with capital F, we take the derivative to get capital F prime of x. If we go back the other direction, if we start with capital F prime of x, taking the antiderivative will get us back to capital F of x. So the derivative and the antiderivative are essentially just opposite processes. So using this notation, we could write the antiderivative of 4x cubed dx is equal to x to the fourth plus c. The reason being that the derivative of x to the fourth plus c is 4x cubed. So the 4x cubed is the integrand, which is just the derivative of x to the fourth. The x to the fourth could be said to be the antiderivative of 4x cubed. The plus c, that's our integration constant. So the question arises is, what does this dx mean? Why do we even need it? Well, the dx indicates that the variable in the problem is x and not some other variable. So when I check to see that the antiderivative is x to the fourth plus c, I'm assuming that the variable is x. And that's what that dx tells me. Because if I were to take the derivative here with respect to something else, then the derivative would be 0, and that wouldn't make much sense, because we'd be assuming then that x was a constant. So what is the difference between the indefinite integral of 2ax dx and the indefinite integral of 2ax dA? So let's look at these one at a time. So when I look at the indefinite integral of 2ax dx, what I'm trying to decide is the derivative with respect to x of what is equal to 2ax. And thinking about it, I realize that the derivative with respect to x of ax squared is equal to 2ax because the derivative of x squared is 2x. The a in this case is just a constant. So now let's look at the other indefinite integral. So when I ask for the indefinite integral of 2ax dA, that means I want to know the derivative of what with respect to a is 2ax. So now I'm taking my derivatives with respect to the variable a. So the derivative with respect to a of a squared x is 2ax because the derivative of a squared is 2a. When I'm talking about derivatives with respect to a, now I'm assuming that the x is being held constant. Just like in the previous example over here, we were assuming that the a was being held constant. So when I take the indefinite integral of 2ax dx, I get ax squared plus perhaps a constant, and the indefinite integral of 2ax dA is going to be a squared x plus perhaps a constant. I haven't included the constants here because we were emphasizing the other term in the antiderivative.